Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. So we're ready basically to start with equations, right? In the sense that we've kind of looked at pictures and we've discussed that what sort of phenomena are we talking about when we say turbulence, right? So now the point is that I still need to calculate things, I still need to evaluate things, right? And the only way I'm going to be able to do that is by writing out equations, right? So, I mean, what is the basic equation? Well, Navier-Stokes equation, right? And I think you should acquaint yourself with the basics of that, how you derive that, what exactly are we talking about, what does this equation mean, what does each term in that equation represent. You should acquaint yourself with that for any standard book, right? It's I think essential that you do that. Okay. Now so I think just now, as I said, what does each term in that equation mean, in the Navier-Stokes equation mean? Or for that matter, you can take any equation, right, of any phenomena that you're going to consider. So each term, has a physical meaning, right? And it's a physical process that we are trying to analyze using equations, right? We're trying to quantify that. It's actually a physical process, right? So how do we, so each term should actually mean something, okay? So there are terms, like this, for example. You will see something like, say, you'll see some things, like this, right? So in terms of a fluid phenomena, what would this physically mean, right? So I'll just talk about that briefly and then go on to the equations that constitute, with which we will be basically analyzing turbulent flows, okay? All right, so let's just do this here, okay? Now, let's say I have a fluid element, right? I'm drawing an axis system. That, okay? And say this is actually an elemental or an infinitesimal, differential length dy, okay? And essentially what is going on is, there is a, fluid flow which is happening, right? And given an axis system, three-dimensional axis system, this is basically the y component that I'm looking at, the velocity in the y direction. So then I'm going to call it this v, right? I'm going to call it this v, okay? So then let's just say that fluid is moving. We call this at this location, right? So what will be this, right? What would be this? Well, let's just say that V2 is going to be V1, right, plus del V del Y, right? How much the velocity is changing, at what rate the velocity is changing in the y direction, right? The rate of change of the velocity in the y direction multiplied by the net length over which this change is happening, so that it will give me the total change in velocity as I move in the direction of flow in the y direction, right. So, then that, okay. In this case, of course, we have said V1, we have set this to be 0, okay. So, therefore, V2 is essentially right. So, we have the change in the velocity, which looks like this, right. Now, every time, right, this term, every time V2, right, is a positive value, right. If this is a positive value, which means what? Which means that if I actually move in the direction of y, there is a change in the velocity, right. So, there is a definitive rate of change of velocity in the y direction, right. And this is when this happens, then what we call this is basically what results in is vortex stretching, right. This is vortex stretching, okay. These are phenomena. So, in the sense that when you encounter something like a turbulence, right, and you are going to consider a fluid particle, what sort of deformations or what sort of changes do those particles undergo, right, as they move? And you've seen like really chaotic and really unsteady, irregular movements, right. So, which is the picture that we saw yesterday, right, in the last lecture. So, then what does that mean in terms of each particle? What is each particle of fluid doing, so that the macro flow looks like that. So, one of the things that you would probably encounter is vortex stretching, okay. So, if you encounter a term like this, del V del Y into dy, something like this, right, and this is a positive value, that means the vortex is being stretched, okay. All right, let's try another case, okay. Let's try another case. Now, let's say I have again a fluid element, okay. In the basically it's the same axis system that I am talking about. Okay, and it's just that this is TC, right. Now, then here it was vortex stretching. Now, let's just say now the vortex does this movement. Right. Now, if it does this, then again I am again talking about V1, right. I am talking about the velocity in the y direction. I am talking about the velocity in the y direction, okay. So, again let this be this, and if this is V2, let us just say this is V2, what is this, right. So, could I say that this is V1 plus del V del C, rate of change of the y component of velocity in the c direction, right, multiplied by the total length over which this change is happening, which is dc. Right. So, again here this one I have set as 0. So, therefore, this is equal to del v del z into dc. Right. Now, this is essentially, if this happens again and if this is a positive value, right. So, something like this. Okay, one more thing is that my flow is again, this is the velocity that I am considering, right. So, what is the difference between, say, picture A and picture B is that in picture A I have considered a fluid element which is in the direction of the velocity that I am considering at this point of time, which is the y component of velocity. In picture B I have considered a velocity, a fluid element which is in a direction which is perpendicular to the direction of velocity which I am considering at the moment, which is the y component of velocity, right. So, it is interesting to see how, if there is a change in the velocity v, right, as we go along in the y direction, right, then how will a fluid particle behave, right, how will a fluid particle behave. You could draw parallels of this, right, with how a boundary layer profile would look like, right. If you see the velocity that I have taken here is at the distance dz. So, I could have taken that velocity here or here or here or here, right. What would be that value, right? What will be that value? How will I calculate that? Okay. So, I leave you to sort of dwell on that and think about it. Okay. So, now this is a phenomena. When that happens is essentially what we are saying this is vortex turning. Okay. This is vortex turning. Okay. So, similarly, right, you could, we could do another, just to sort of do another case. I am looking at V, right. So, you could look at x also and look at the u component, the u component of the velocity or the w component of the velocity, which is in the z direction, and look at the effect of that, right. For example, what would be, say, w1, which is the velocity. So, if I am going to consider velocity in the z direction, this is for A that I am talking about. If I am going to consider, say, velocity, right, in this direction, which is, say, w, right. So, and here of course, w1 is 0. Let us just say w1 is 0. What would you what could be the value of w2, right. So, in this case I would think that w2, right, w2 is equal to w1 plus del w del y into dy, right. So, so essentially what I am trying to say is, if I am considering, right, okay, now the point is w2, right. Now, say this w2, okay, that I have just written here, okay, and again this one is, say, 0, okay. So, then my w2 becomes del w del y into dy, right, is that right? Okay. Now, so essentially this is telling me that the z component of velocity, right, is going to be equal to the rate of change of z component in the y direction into the length over which that is happening, which is dy, right. Now, if this happens, what do you think it is going to do? So therefore, say this is positive. If this is positive, then what will happen to the fluid element? Think about it, right. So, this is z component is in which direction? It is in the z direction. So, that means if the w1 is 0 at, say, 1, right, at this location it is 1, and this is the 2 location, isn't it? So I have a positive W2, which means this fluid element is obviously going to be moving in the z direction, right? If there is a net W2 direction, which means that I could possibly have, let's just do that, okay? I could possibly have something like that. Right? So I would probably have something like this, and this is going to be my W2. Is that right? So therefore, the W2 in this case, right, the z component of velocity in this case is going to cause turning, right? So if I take a velocity, if I take a fluid element in the y direction, right, then the W component of the velocity, which is in a direction which is perpendicular to the axis on which this fluid element exists, right, and that is going to cause a turning if I have a net W2, right, at the far end of the fluid element that I am considering, right. Okay. So similarly, so if that being said, right, if I come back to B then, right, if I come back to B here, so now if I again consider this velocity, right, this is my W, right, so then I will probably, this one, the green, right, so I say it has been turned, right, by the velocity v, so that what will the W do, right. So I will have the same thing. So here I will also have a W2, right, and in this case, right, and in this case the W2, right, is going to be W1 is 0, okay, W1 is 0, del W del Z into dZ, right. Right. So this is, and if this is positive, then this actually causes stretching, right, whereas here this, if it is positive, then this causes turning. Makes sense? Okay. So now you could I leave the x axis to you, okay. Why don't you figure out what that will do, right? Just figure out for yourself, if I consider the velocity in the x direction, how that is going to behave and what is that going to do, right? So in the sense, you take x and z and x and y and see what that's going to do, right? So okay, so that's what I want to talk about. So if you have terms like this, right, you should be able to look at this and figure out what these things mean. Okay. All right. So now get on to what is specifically for turbulent motions. Now I've been talking about a velocity profile. We talk about velocities like this. So we talk about right. So I could have a velocity like this, right, and where all the components basically are functions of space and time. Right, all the components of functions of space and time. Okay. Now this is a typical velocity profile that we know, right, and we can plot and we can do things. And just now I said that del u, the terms like del u del y, right, where del u del z is going to cause turning of a fluid element, whereas del u del x or del v del y is going to stretch the vortex, I mean fluid element, right. So that's what we just said. Okay. Then how is it that we take the same velocity and represent a turbulent flow? What is it so different about turbulent flow? What is it that we we have to take into cognizance to in order to write out these equations? Well, the difference or the essence of a turbulent flow is essentially that it is random, it is chaotic, it is unsteady, and it has motions that I actually am not able to define in a regular pattern with something very a known function, nothing like that. It's very random, right? And it's fluctuating, right? I think that's the word. So it's fluctuating at every second, at every instant of time, as well as every space that you can get to, right? So what we do here, so therefore what do we do? If I have a turbulent flow, then how do I represent it? Okay, so we do what is typically known as mean flow equations, right? We basically mean that it is mean flow equations. Okay, right. And this is, so we'll do what is basically known as the Reynolds decomposition. So the Reynolds decomposition is essentially okay. So this component of velocity in the x direction, which we say as u, right. So this we write as a mean value and a fluctuating value, a mean value and a fluctuating value. Okay. So therefore this mean value of the velocity what do we mean? I mean, what do you mean by that? What exactly are we doing? So what we essentially do is, it's easy, you go from right. Does this make sense to you? So essentially what I'm saying, if I'm going to write this in a discretized form, let me do that, see if it will make a little more sense to you. So essentially I could write this as a summation, right? I could write this as ui delta t, right, delta ti summation I is equal to 1 to n, right, and this whole thing is by, well, it's actually t, right. I have a flow, right, and I'm looking at the horizontal, I mean the x-axis, x component of the velocity, right. I take a time instant, I discretize that over small instances of time, and over each of those times I calculate the, I take the velocities, right. I just do that, and then I divide, just take an average of that, right. So which is this mean value? This mean value that I'm talking about is just that, right. So this is what we essentially do. Right. So then the decomposition, therefore the total velocity, what we say is that therefore I have, so essentially what I'm saying is my flow, total flow is, so say this is my time, or rather this is my time, and this is my u component of velocity. So what will happen is I will have an average value, right. So which will be u bar, which is like a single value, right, single value, and over and above as I move through this time, I will have fluctuations like this, right? There's nothing orderly, nothing regular, it is unsteady, it is chaotic, everything, right? So I do that. So therefore, for example, at a particular location, right? So at a, for example, at this location, say, at this instant of time. So say this is, say, TA, right? So what do you think is going to be the velocity? So this is my fluctuation. This is my, this value, right, is my u dash, right? U dash is the fluctuation, right? So therefore, at this TA, so let me call that as u dash a, right? So here the velocity, so ua is basically equal to this plus u dash at a, right? So similarly, if I have, for example, say here, which is say TB, right? So here, let's just say this is UB dash, right? So where, so therefore UB is equal to this plus UB dash, total velocity, right? So therefore, the fluctuation is essentially with respect to the mean values, right? So I could denote it this way. This is my UB dash. Okay. So similarly, I could also have, for example, a location like this, right? And this is UC dash, right? UC dash, and say this is this, right? Then UC is going to be this minus UC dash, right? So on and so forth. So this is essentially what we mean by, so therefore this is what the velocity u, for example, matter for example. So I have a mean value, and to which I add the transient or the fluctuating values, right? So therefore you can see that as I move in time, so this, when I say A, B and C, these are actually different instances of time, right? And therefore your velocity is different. Okay. Okay, so now the so essentially that, okay. Okay, one more thing is that now what's a good size? What's a good size of the sample that of the flow, which will give me more or less correct mean value? You know, you have a fluctuating, you know, very random, very irregular, chaotic, unsteady motion. We try to get a mean picture of that, right? But how long? I mean, what's a good size of time that I should take? You know, which should give me a correct, more or less a correct mean value of u, right? So if I do that, that is important, right? So in that time instant, right? So whatever fluctuations I have, so for example, if I look at this picture here, right? If I look at this picture here, so I keep doing this, right? I took A, I took B, I took C. And the point is, how long will I do that, right? So I will make sure that I capture sufficient number of fluctuations, right? Sufficient number of fluctuations. For example, what if I did just, what if I just looked at this much? Do you think it would give me a very nice idea of what is, or for example, I would just choose this bit, you know, or for example, just this bit, right? Or say this, it almost has no fluctuations there, right? So if I were to do that, then it would not give me, give me, you know, a correct assessment of the fluctuating flow itself, right? I'm trying to understand that. So I will take my t value such that it is large enough. It is several times larger than the time the period over which a particular fluctuation can repeat, right? So essentially what I'm saying is we will take a time interval such that it is significantly larger, you know, to capture several fluctuations, so that it is in a given time duration interval, sufficient number of fluctuations which are captured. Okay. Right. So, what I mean by that, right, is that, for example, yeah, this is a good example. For example, in wind tunnel, for example, right, what should be, for example, a time period. So, essentially we do this, we calculate the velocities at say every second, at every second we look at that, right. However, in an ocean, for example, in an ocean or in an experiment where you are generating waves and trying to look at that, what sort of time interval should we look at, what should we? So, there a minimum like about say 20 to 30 minutes about 20 minutes is actually minimum, right. You understand what I am trying to say here. So, in the sense that if you want to get a fair enough picture of the ocean surface, right, then you should be sort of averaging data over say 20 minutes to half an hour. You drop all that data and then you show the data and when you plot it, basically it's every 20 minutes how it looks like, right. Then it is sufficiently. So, therefore, if you have to take make so data, so you can understand the tremendous large amount of data is going to be required, right. You have to sit there for like 2 to 3 hours maybe, just really exaggerating it, I would say, but let's just say you sit there for like 3 hours, right. You collect data and then you plot it. You show that you can basically see differences, or you can see fluctuations, right, in every 20 minutes or 30 minutes, like that. Okay. Whereas a wind tunnel, 1 second is very essential. Sometimes even less. Depends on what kind of flows you are looking at. If you are looking at a high angle of attack flow, right at the time where it's going to separate, it's highly unsteady, and that is the time sometimes we try not to go even like change from say one angle of attack to the other. We go by like half an angle or even less, right. It's difficult to do, but then that's what one would expect. One would like actually to sort of get more data, as to the changes, because the changes are very, very, very sharp. Okay. Okay. So, of course, this I think I should write in the previous slide here. So, as you can see, so these are essentially the changes. So, therefore, now if you see here, this would be by definition. So, in the sense that I define basically the deflections, as deflections from mean values, right. So, therefore, this is by definition, right, the mean makes sense, because I said that this is the value, right, this is the mean value and I am fluctuating above this. So, if I take the mean of this thing, then it should fall on this black line, right. So, this black line is nothing but this mean u bar here. Okay. All right. So, this is okay. All right. Now, okay. So, now having spoken on these terms, now again to characterize the numerical magnitude. So, now we spoke about we wrote down how we are going to calculate the mean value. Now, we are trying to concentrate on the fluctuations, right. So, to characterize the numerical magnitude of the fluctuating value, right. So, what we could do a few things. So, we could write that as, so this is numerical, so characterization So let's just write characterize the numerical magnitude of u dash, right. So, what do? We do that. That makes sense because some are negative, some are positive, right. T naught plus this, right. Simply we just take a mean of these squares, right, the squares, right, or we could do that, or we could just write, we take a mean of the fluctuations right. We just take a modulus of we just take the absolute values and just sum them up, right. So, practically the u dash square, right, this one is measured easily and relevant mathematically, right, since it is directly related to the standard deviation and probability density distribution of u dash. Well, statistical analysis is not my forte really. I don't understand too much of it. So, I'm not going to get into that too much. Okay. Now, so having spoken about this, now let me sort of I'll just sum this up a little more before we start going at the equations. Now, now that I have written this, okay, okay, so I've been writing T naught and T naught plus T, right. So I'm saying sum it up over a certain time scale. Okay, that's what I've been saying. Now, what do you suppose? What do you suppose? So essentially, what I am saying is that this is actually T naught. Okay, and then I had to start somewhere, so I take T naught. So, would you ask me? Would you ask this question that where should T naught be? Should T naught be equal to 0? This is time, So, if I start at different times, would the mean values be different? In the sense, would I see a different type of turbulence, or what is it? Right. Now, so in that sense, basically the point is that you can essentially, we are assuming that for example, the turbulent intensity, right, say the amount of turbulence, crudely as of saying, so that would whole probably exist at all times. Right, the turbulence is existing. We are basically assuming this, that the turbulence, the behavior or the nature of the turbulence is not going to be dependent on T naught, and the turbulence is going to be there at whatever instant of time you decide to start with. Okay. So, however, when I start out with a certain T naught, right, so this is a time variant thing, we are writing it out as a time variant thing. We are showing it, we are showing the value as how they differ with time, right. We are doing that. So, even if I go up till say T, right. So, therefore, I will have information till about T naught plus T, right. Now, if I need to sort of figure out the information right after that time instant, right. So, will the information about that we received at this time, this time interval, right, would that sort of would that be relevant, right. So, what would I do that? I mean, would that be relevant? Well, they should kind of, I mean, we'll have to see, you know what I'm trying to say, that I am taking, for example, I am taking this look at this, right. So, say my T naught, so T is here, T naught plus T is somewhere over here, right. So, when I take this information, will that be applicable over the next one, right. So, now at this point of time, we are basically assuming yes, right. We are basically assuming that no matter where you start, right, you get more or less a fair picture of the turbulence. Okay. So, that is what the meaning of T is, okay. The time interval is. Okay. So, so now the point is this. Okay. So, the point is that we have the velocities. So, similarly, let me say, I think I should write this down, right. So, if I were to write this, so let me sort of jot down a few things. Okay, let us go to the next page. So, let us just say, so how do you study turbulent flow? One is statistical analysis, and the other is mean flow properties, which I just described. Okay, so let us just see what we sort of mean by that. So, we have turbulence, okay, and you have a statistical analysis, right, and this is the mean flow properties. Okay. So, here, so statistical analysis, basically we analyze the fluctuations themselves, right, itself. So, what we do is analyze the fluctuations themselves, right. So, then we can calculate RMS values, the frequency spectra. This is a good way of knowing what sort of fluctuations are sort of happening. What is the chance that this particular fluctuation is going to repeat itself, and at what intervals. Okay. So, that is why the frequency spectra, space time correlation, of course. Yeah. Is that right? And again, interaction with each other. Okay. All right. What about the mean flow? Well, so we're basically predicting the gross properties of a turbulent shear flow. So, in this case we look at, or say, predict gross properties, right. So, which is this, skin friction, boundary layer thickness, boundary layer displacement thickness, skin friction, heat transfer coefficient, so on and so forth, right. So, now, so essentially I think, okay. So, now I will draw this, and then we will kind of call it a day. Okay. So, let us say this is t and this is the u component of velocity. Okay, and I am going to do that. And this, I am just repeating this, it's the same thing. Okay. Now, what if you see this plot? So, let's just look at this. Let's just look at this plot here, plot A. Okay. So, in this bit, right, till about say here, till this t, would you say there is no change in the velocity as we change with time? So, I could say this bit is steady. Is that right? This here, the other part is unsteady. Would that make sense? Yeah? Okay. Now, fine. So, I have the same plot here. I have the same plot right here. Okay. Then, if I were to say this is laminar, as you see it now, right? How would this be different for a turbulent flow? How the same picture would be different for a turbulent flow? This is going to be the only difference. The turbulent flow will be something like this. That's all, right? So, same thing, this is also in the steady state, in the unsteady state, but you have to make a distinction between fluctuations and unsteady flow. Okay, I think at this point of time it's important to say that. So, again, so here till this part it is steady. What is steady? Just now we said that what exactly is how is the turbulence going to repeat itself or what, right? And here it is unsteady. So, if this red line that I have drawn here, if you consider that as say u bar, right, is so the red is essentially the mean value, right, and the blue is essentially the fluctuating part, right. So, therefore, your total velocity, right, total velocity is, yeah, as here, right, this is your total velocity, which is essentially you write that down as a mean value and a fluctuating value, right. Okay. So, essentially that, so if you do that, so if you have a mean value and a fluctuating value, so therefore, now the u plus u bar, if you look at this u, now that is not changing as we move here. Would that mean the mean value is not changing? Would that mean the u fluctuations are not changing? Well, we'll figure these things out maybe as we go along. Okay. So, this part, the second half of this is unsteady. Okay. If I may erase this bit, okay, this part is unsteady. Okay. So, when this is unsteady and these are unsteady fluctuations, right, you also have fluctuations right here, and it is unsteady in the sense that u dash is not constant, it's not fluctuating the same way over the entire time scale, right. So, that is why it is unsteady and it is fluctuating, right. Okay. So, I think we are going to stop here, except that let me just write out some of the terms, okay, and then we will just stop. So, essentially when mean flow, when I say mean flow, so I am talking about say velocity components, which could be this plus fluctuating part, this okay, then W is this temperature, this. Okay. So, I here and we start equations, the equations which are like continuity equations, and when you have the velocities, if we use, which is what we're going to do now, how do the right, and where we will develop equations for turbulence, right? Stop now and see you in the next class. Okay, thank you.